Hello, everyone, and welcome to the VaNTAGE seminar. So we're continuing our series on machine learning and number theory. And today we're very happy to have Francois Charton, who will be talking about mathematical discovery, watching a model learn. And Francois, is it all right if we record this talk?
Yep, it is.
Wonderful. And feel free to ask questions during the talk. Okay, please go ahead.
Okay, thank you very much. So I'm Francois Charton. I work in a startup named Axiom that does AI for math, and I'm also affiliated with the ENPC, École Nationale des Ponts et Chaussées, the French National School for Bridges and Causeways. Um, and I'm interested in, mathematical discovery. So I want to show the result of a recent experiments, which is, how you can do mathematical discovery basically by training a model and watching it and deriving a few what I think could be interesting intuition from this. Um, so if you think of usage of AI in mathematics these days, the most famous, the thing that everybody is talking about is usually formalizing mathematics and proving theorems. So that's using lean, using tools that could be using AI to accelerate lean, etc. And maybe using AI to auto-formalize theorems, so write into lean, theorems that are written in standard English. Um, Also, there's a second area, field of research, which is about coming up with conjectures, how you could use probably lean to design new conjectures that you don't know and then try to prove them. And there's a whole different area that try to generate examples, counterexamples. This is pattern boost, this is alpha evolve and all the evolve family. So that's quite an active thing. So I want to talk about the different approach, which is, suppose you have a hard mathematical problem that you've thought a lot about. Is there a way to use AI to try to acquire new intuitions about this problem? So to sort of brainstorm, if you wish, if you will, with AI. So I'm going to show this on one example, which is a very, so this is a paper that was published a while ago. So I want to talk about a very famous problem, which you most certainly know, which is the collapse sequence. So basically, the collapse sequence, you start with a positive integer, say n. If it's odd, you multiply by 3, add 1, divide by 2, so you get another integer. If it's even, you just divide by 2. And then you get a second integer, and you can repeat, and you get a sequence, which is known as the collapse sequence. And it's the home of a very famous conjecture, so it's been very well studied. The conjecture is not the subject of this talk, but it was motivation, and which says that all these sequence end up reaching one at some point. So I'm going to talk about a feature of the collapse sequence, which are called the long collapse step. So the long collapse step says, okay, it's a way to make longer steps along the collapse sequence. So suppose you start with an odd number. So your number n is odd, you start from an odd number, and so the first step is going to be n2, 3n plus 1 divided by 2. Okay, you're going to do that. So you repeat this number so long you reach an odd number. So long you can, you do n times 3n plus 1 on 2, n2, 3n plus 1 on 2, and you're going to repeat that a number of times that I call k. K is a function of n, different n have different k's. And at this point, you reach an even number, which you will divide by 2 for as long as you can. So until you reach an odd number. And that's k prime time. Okay, so practically, if you start, say, with 11, 11, odd number, you can multiply by 3, add 1, divide by 2, you'll get 17. This is still odd, so you do it again and you get up to 26. And this is the end of the up, move, n to 3n plus 1 on 2. And at that time, you can say that k, the number of up steps is 2. And then 26, you will divide by 2, but you can divide it only once to 13, and k prime equals 1. So the function I want to learn is this function that goes from 11 to 13 by going up along the collapse sequence for as long as I can, and down, by dividing by 2 for as long as I can. And the question I'm going to study is, could a transformer learn such an arithmetic function? Is it possible to train a model from an example to predict, the long collapse successor of any odd integer? So you might wonder why I care about that or why this could be an interesting problem. So there are two branches of reason. There's a first set of reason which are more AI or computer science related. It's been known for a while that transformers struggle on arithmetic with large integer. It's very tough to train, say, a large language model to perform multiplication of no, long numbers. So, yeah. So it's difficult to learn basic arithmetic. So, a complex arithmetic function like the collide successor might be an interesting challenge. Can a transformer learn that? Or are we completely doomed? There's no way to do exact arithmetic on a transformer. And also, I've been noticing that previous results, so I had previous results on GCD, on modular addition, so on not too complex arithmetic, but they always feature functions that have only a few outcomes. So basically, what the model is doing in that case is very close to what you could call pattern recognition. Basically, you give an input and you have a small set of possible outputs to select from, either the sum modulo something, so only as large as the modulus you have. In the case of GCD, you can have all kind of GCD, but most of the GCDs are very small. Or, Möbius function. I know Jordan worked on Möbius function and stuff like that. So it's interesting here because we're studying a much more complex function. It's a regression-like setting because the function maps, a large set of integer over another large set of integers. So it's not a many to one or many to few function, but many to many. Um, Another good reason of studying that it's known that deep learning models struggle with, compositionality, complex algorithm. Every time you have something that is made of different parts, you want to add and then multiply and then do this and then do that, the model usually lose track after one or two steps. Same goes for loops. Every time you have a loop, if the loop is a bit long, the model usually has difficulty learning it. So in this case, it's interesting because it's a fairly complex algorithm. It's basically two loops. You have n2, 3n plus 1 on 2 that you repeat k times, where the number of passes through the loop k is a function of n, so varies depending on n. And then you got the second loop, which is n divided by 2, where you make k prime passes, again a function of n. Okay, so these are why, as an AI researcher, I was sort of interested in that. It's complex, it's compositional, and it's a regression, so it's a fairly hard problem, supposedly a fairly hard problem for a model. Um, sorry. There are also a couple of interesting mathematical reasons. So the first thing is that it's a new problem from AI. There's in AI this very strong benchmark mentality where everybody studies on the same problem at the same time. And it's a bit boring because you end up studying very well three problems or four problems that everybody wants to do. And so it's interesting to work on something new. It's also what I would call a provably hard problem. Collapse sequences are very simple, but they're known because of the conjecture to give rise to very complex behavior. So it's not an obvious problem that has an unknown problem that has an obvious solution. It's something that is, known to be complex. And also because of the conjecture, again, there's a ton of theoretical results that have been, accumulated throughout years and that we can try to rediscover. So it's a good benchmark, if you like, to try to understand, what a model, what a transformer can do on a fairly hard and well-studied problem. Okay, so the goal here is I want to train my model to predict long collapse steps. And the thing I'd like to show is whether we can learn or rediscover some of the deeper mathematical results that are known about collapse sequence just by, training the model and watching the results and deriving conclusion from what we learn. So this was a paper from last year published with Ashni Narayanan, who's a postdoc student in Sydney Mathematical Research Institute with Jody Williamson. And it was actually started more than a year ago during that seminar, that program we had in Harvard in CMSA. And it was published last year in 2025, so you got the archive elements. So the paper is no, and I'll explain why transformers know more than they can tell, and it's all about learning the collapse sequence. So what I am going to do, so I need a training set, so I'm going to generate, I know how to calculate the collapse and the long collapse steps. So I'm going to generate pairs n kappa of n for n odd. So I generate random odd numbers and I calculate their Collet successor. So that number that is, a number of steps after them on the Collet sequence. And I'm randomly choosing numbers from between 1 and 10 to the 12. So I have 5 times 10 to the 11 possible pairs. So that's a huge problem space. So there's no way the model is going to memorize anything. There are way more example than there will be example or possible example than there will be example used. And it also eliminates, the risk of duplication between your training and test sets and memorization and all that. So I'm going to generate all these pairs. I'm going to encode them as sequences of digits in some base. And most of the experiments will rely on changing the base. So basically the input is an integer, the output is another integer, both odd. And I can encode the integer as sequence of digit in base 2, 3, 4, 5. I'm going to experiment in all base between 2 and 57. Um, Finally, I have 56 different cases, and I'm going to use these generated pairs encoded as sequence of digits, input and outputs, to train 56 encoder-decoder transformer, so one per base, to try to predict kappa of n, so the long collat successor, from n. Okay, so the models are really vanilla garden variety transformers, encoder decoder is the original transformer model from Vaswani in 2017, I think. They're relatively small models, so I got 4 layers in the encoder, one in the decoder, 5 12-dimension, 8 heads. It uses Intuit, which is an open repo that you can reuse. And when trying to predict, kappa of n from n, when trying to predict the collat successor, the model is doing no mathematics. It's just trying to predict the next word. It's just a letter game. The model is basically trying to translate the input, a sequence of digits, into the output, another sequence of digits. Okay, so you generate pairs, you train the models, and every once in a while, you generate 100,000 random examples, which, because of the size of the problem space, will not or mostly not duplicate with your training data. So new examples. And you check whether the model can predict the successors of those 100,000 examples and see what happens. So success here is very simple. Either you predict correctly or you don't. So there's no, points for being one off or two off or three offs. It's perfect or not. It's a very large problem space, so there's no question about, memorization, contamination, grokking. All this doesn't exist, so it's simpler, if you will. And just to be sure, I'm running, every time I test a model, I'm running a different test set at each epoch. So the good with that is that you're not working on a single test set. So if your test set, your random test set sort of duplicated with your training set, etc., well, the next epoch you will have a new one, so everything is fine. Okay, so this is the thing I'm going to do. Um, so the first try was just training those 56 models. So to predict this function, so since a few people have come a bit late, let me explain what I'm trying to predict. It's the collat sequence. So you start with an odd number. You transform this odd number by doing n to 3n plus 1 on 2 as many times as you can, this k times. And then you reach an even number and you divide by 2 as many times as you can, k prime times. And you're back to an odd number. This is the function I'm trying to predict. So the first thing you do is that you're going to train those 56 model. You give them a whole lot of odd numbers. You give them the long collat successor of those numbers, and you see if the model is able to predict them. And you measure this as an accuracy. So I have 100,000 examples, and I want to see how many of those examples my trained model is able to predict. And the first thing, which was a big surprise for me, is that it seems a very, very easy problem. So two of my models in base 24 and 32 achieve 99.8% accuracy. Well, 99.75 to be precise. So it means on 100,000 examples that the model hasn't seen during training, my trained model is capable to predict perfectly all the examples I shoot at him except 250. So that's really a lot. And if you look at other bases, so why base 32 and 24, you might think that It's a high power of 2 times 3 or a high power of 2. And the collapse sequence has those number 3 and 2 inside it and the notion of parity. So it seems logical that those Bayes might work. But still, the level of the result is very surprising, considering the fact that transformers usually struggle with, basic integer multiplication. So it's very surprising they do that. If you look at all the Bayes results, so that's table one, you can see that the best bases that achieve more than 99.5% accuracy are usually high powers of 2 or products of 3 times a high power of 2. So 8, 48, 24, 16, 32, etc. Then if you look the even base, almost all the models in even base achieve more than 90% accuracy. And this is, in an even base, you can test parity, and parity is important to the collapse problem. So there is a certain logic that even base work well. The stranger thing here is that odd base work very well as well. So you see odd base model, so the lowest one are around 25%, but a lot of models, odd base model achieve 80, 70% accuracy. So which means that, out of 100,000 test example, the trained model can predict correctly 70,000 or 80,000 of them. So that's really a lot. And this again is surprising. Another thing that you can see here is that if you look at the accuracies of the trained model, the values for different base tend to cluster around a small number of values. There's 5 models that are within 1% accuracy between 81 and 82. There are like 10 different models, 11 actually, that are between 70 and 71, and nothing in the middle. And, around 50, 55 and 56, there's a lot of models as well. So this is strange because, whereas, it's surprising that different Bayes would learn, there's no reason why the same accuracies would be achieved by different models using different bases. So a way to look at this is to look at the learning curve. So this is the figure here. The learning curve, basically the x-axis is the performance of the model on a random training set. So every 300,000 examples, I call that an epoch, I run a new test set and see the performance of my model and record it here. And the x-axis is just the number of epochs. So it's how many times I run, how many examples I show the model. So here I'm training, on 300,000 examples. So, millions of examples, one after the other, new examples all the time. And these curves are interesting because you can see these are the curves for all the 56 bases. So they have two characteristics. The first thing is that they have a step shape. You don't learn progressively an accuracy that would go up slowly person by person. The accuracy moves in steps. So it's flat for a while and then it moves to certain values. So this discrete learning is something that you observe, commonly when you do math with transformer. I can't quite explain it, but it's a fairly common fact about mathematics with transformers, which seems to suggest that the model is learning by, discrete step. Well, all of a sudden the model gets something about the problem and learns a new thing, or the model moves from one local equilibrium into another, etc., in discrete steps. The second thing that is way less obvious is that accuracy levels are quantized in the sense of quantum physics quantized. Basically, they only take a few values. If you look at my curves, not only does it look like some kind of strange staircase, but the steps are all at the same height. And I will restate here that, the models you see here, the 56 models, encode the integers in completely different ways, in different bases. So, the base 7 model and the base 17 model happen to end up with the same accuracy, even though the numbers they encode are totally different. And this is a new pattern. This has not been observed in previous experiments. And the fact that it seems to hold for all problems, for all bases, suggests that it could be a property of the problem and not of the representation. So this suggests we might be observing, models that are learning a property of the collapse sequence, not a property, of the model or base 5 representation or something like that, because you get the same pattern happening everywhere. So the next order of business when you see that is to try to understand what's happening with these steps and what justify those quantized accuracy. So the way you can do that is that you can just, you try 100,000 examples, and then you try to classify the correct prediction and the wrong prediction. And if you want to do this, you will soon observe that the quantized steps correspond to special classes of inputs. Basically, every time you have a model performing at a certain level of accuracy, and you run it on a lot of test example not seen during training, you will see that there are classes of examples which are inputs that correspond to specific residuals modulo 2 to the p, or if you prefer in binary notation, inputs that end with a certain binary and in a certain binary sequence or binary suffix. So for these models, the model predicts, for these inputs, the model predicts the collapse next step in with 99% accuracy, so almost perfect. The model makes almost no errors. And on all other inputs, it's always less than one. So the model is in a, if you like, in a way binary. The steps you see happen because at some point the model figures out a whole class which can be defined as input with a certain residual modulo 2 to the p and learns to predict it perfectly, and all the rest is not learned. And the steps is as you learn new classes. So specifically, you have a learning pattern here, which is independent of the base, which says that all the models start by learning to predict all input ending in 0, 0, 1. So that's the inputs congruent to 1 modulo 8. Okay? And they learn those guys first and learn to predict their correct successor very well, 99% accuracy, which result in this 25% accuracy that you can see here, the first step, the green step that you can see at the bottom of the curve. Then after a while, the models are learning all inputs ending in 1011. So these are, I don't know, something modulo 16, 11 modulo 16. And added to the previous one is 37.5 accuracy, which is the second step you see. And then after a while, they figure out 1101 for 50% accuracy, etc. In other words, there is something that I call the learning pattern, which is, a set of input. The model is learning the collat's successor, one class of input at a time, independently of how the data is encoded. And the effect of having a base or another is just it accelerate or slows the process. So some bases are slower, some bases are faster, but you get the same steps. So why do you get these residual classes? Why you learn, one group of input at a time? Uh, So, the pattern is like that. You have a sequence of binary ending or residuals modulo 2 to the p, and the model learns those class. And once a class is learned, the collapse mapping is predicted almost perfectly. These are the steps. And it seems that performing the arithmetic calculation is not really the problem. The problem is identifying, the classes. So interestingly, you can show that these classes correspond to special value of k and k prime. You remember k and k prime are the lengths of the two loops in the calculation of the long collat steps. So the first class that is learned, 0, 0, 1, correspond to all the input and only the input that have k equals k primes equal 1. And the second class have k equal 2, k prime equal 1. And the third one has k equal 1, k prime equal 2. In other words, what the model is learning is the model is gradually figuring out classes of input that correspond to a number of passes in the loop of the algorithm. So, you have this two-loop algorithm with a variable number of passes in the loop. So the model first figures out all the cases and just those cases where k equals k prime. So you have one pass in the first loop, one pass in the second. Then it gets two pass in the first, one in the second, then one pass in the first, two cases in the second, and so on. So this is how the model learns. So this is interesting because it states something. It says something about the collat sequence that I didn't know, and my mathematician colleague didn't seem to know, that the lengths of the loops k and k prime seem to be encoded in the binary representation of n. So for k, it's very obvious, the number of passes, the first step, you can very easily show that it corresponds to the number of ones at the right of the binary representation. So learning this is not difficult. If you have the binary representation, you just count the ones, and this is the number of steps in the first loop. But the number of divisions by zeros, by 2, that you have to do after this set of transformation is less obvious. And we could show that there's a theorem, we could prove a theorem that showed that actually you could have a 1-1 mapping between the possible binary endings and the value of k and k prime. So, you could deduce that. So we were quite happy of having found the theorem, which is a relatively deep theorem, which then we discovered because I was called by Alex Kantorovich, who had seen the paper and said, Let's talk about it." And said, this, what you found is related to something we had proven a couple of years before with Jakob Sinai uh, on, you know, on the structure of the collat sequence. So they use a different definition of the long collat step, but something very related. They hadn't found the same kind of sequence. So I was a bit sad, of course, because my great theorem had been found by someone else. But I was quite proud because it showed that this was a fairly deep property of the collat sequence that had been discovered just by watching a transformer learn and, working on the intuition built by looking at these weird learning curves. Okay, so let's summarize what we've learned. By just, generating a lot of collats long steps, we could train models and we could show that the model is learning the long collat step one pair kk prime, so one length of step at a time, in increasing order of k plus k prime. As soon as you've learned a pair, calculating the actual function, the complex function made by the collat steps, is done in no time. So this is learned very fast. The difficulty is not to calculate the steps, it's figuring out, the length of the loop. Okay. And the model doesn't learn by gradual step, by gradual approximation. Once it learns one pair kk prime, everything is correct and all the rest is wrong. There's no case where the model is almost correct or learns some of the element but not the other. The small values are not. This is not happening. So the model is just basically learning successive mappings. So there's a full mapping of the long collat steps, which is the big function over there, which depends on two parameters, k and k prime, which are functions of the inputs. And what the model is learning is a restriction of this to particular values of k and k prime, so particular classes of inputs. So it's an approximation of the function I want to calculate, but it's a very special approximation, approximation that works by studying increasing perfect restriction of the function on increasing classes of inputs. Okay, so yeah, so this is the first takeaway. It's an interesting thing because you can show here that a transformer can learn a fairly complex arithmetic function, no matter that it cannot learn basically multiplication, and also that it learns it in a very special and counterintuitive way. And finally, that you can use that to rediscover, some mathematics. So it can provide you, an open problem. This could provide you with new intuition that you might not have had. Okay, so
Jordan has
yeah,
an observation in the chat. Jordan, do
yeah,
you want to read it or do you want me to read it?
Oh, sure. I didn't mean to break in. Sorry. I put it in because I
please.
have to leave early. But I couldn't help noticing that the odd moduli that work best, like 33, are the ones that are close to powers of 2. And presumably that's because if I write a number base 33, I can sort of figure out what it is mod 32 by, let's see, is it summing the digits or alternatingly summing the digits? But the point is it's computationally more accessible
Yeah, I
to
suspect
see
I
the.
suspect so. I was never able to prove it very clearly. I spent quite a bit of time because you got 9 also that works well,
Exactly.
but then you got 45, which sort of defeats the purpose, right?
That's true.
And then okay, 15 and 17 are very, very tempting.
And 33 is the best odd number, right? And that's
Yeah,
and that's
so
very close to
33,
32.
absolutely. 33 is a pleasure. The one funny thing I can add is that I run this on different seeds and many times, and I basically get the same kind of result. So there's a special case. 3 is a very bad case, but 3 is a bad case for a good reason. It's just because the sequence are long. When the sequence become long, grow very long, the transformer has more difficulty to learn them. So
I
3
see.
is a bad example, and 5 probably falls in the same category. The small numbers, but not all small numbers. 9 is quite good.
Yes, I remember you teaching me this trade-off about size of the alphabet versus length of the
Yeah.
sequence. This is a yes.
Yeah, you can see it here. It's so let me move on to the second part of what I wanted to say. So the next step I was interested. So the model can learn, with very, very good accuracy, and I learned a couple of things about the collat sequence, which you might know already, but interesting thing I found just by looking at the model. So the next question is, we looked at the correct prediction. What about the wrong prediction? What about error? And I'm interested in error because there's this long, standing idea about transformer, which is they hallucinate. And this is a documented phenomenon, language models sometimes get totally wrong at random and make totally irrelevant predictions. So at one moment, they start, for no very good reason, they start getting totally crazy and saying something totally random. And of course, if this happened in math transformer or in anything you want to do science, it would be a bad thing. It's okay to have something that sometimes fails if you can tell when it fails, and if it fails, if possible, not too far from the correct solution. If you get something that randomly fails and outputs something totally crazy, then it's not good for the model. So the question is, okay, do we have hallucination here? Because the very deterministic structure we have in the learning suggests that the model doesn't seem to hallucinate. The model seems to know what it's doing. And so how do you investigate error? Well, it's very easy. You take a trained model, one of the 56 models we had, well, all of them actually, and you run it on 100,000 random test case that you haven't seen during training in domain. And then you compare the predicted value to the correct value. You know both, right? And specifically, what I'm going to compare is the ratio. I have a predicted value. I have a correct value. I want to calculate the ratio of it and see the values of that. So here's the result, and there's more quantization here. So the errors are shockingly non-random, and I really mean it. So these are two examples for base 26 and base 38. And this is the distribution of the model. And I haven't cheated with the histogram. The bins are very small. So when I say the ratio is close to 2 or 4 or 8, it's within 0.01% or something like that. So really, the errors, when you look at the ratio, you look at all the model errors, and you map the prediction, the ratio of the prediction to the correct value, you see that they have these weird, again, it's a bit like physics, it's a bit like spectra, um, there are preferred values, which seem to be a sum of power distribution, discrete power distribution. So in the first case, you can see, in both cases, you can see 2, 4, 8, 16. So there's a lot of errors that call very for to a power of 2 times the correct value. And then the next values is exactly 126, so 1 times the base divided by this. And you can see next to it, you have 2, 4 in base 38, you have 2 to 38. Sorry, that's a typo. So that's 2 to 38 and 2 third 4 9. So you got values, and these values are not random. So it's very interesting because if you look at the errors, not only are the predictions not non-random, the errors seem to be motivated by something. The model is not failing randomly or predicting randomly. It's predicting something that seems to make mathematical sense. So let's first look at the best case, the best models. So if I take base 24, I said I have 243 errors out of 100,000 test example. So this is cool because I can just look at them. It takes a few hours, but it's doable. So the first thing I notice is that the errors happen for specific input classes, large value of k and k prime. This we know already. This is the learning pattern. We know that these guys are more difficult to learn than the small values of k and k prime. So yeah, no surprise there. But what's more interesting is that if you look at the ratio, the ratio is almost always very close to 1. In base 24, 84% of the errors are within 1% of 1, the ratio, and 93 within 3%. In base 32, it's even better. So when the model is wrong, it's not randomly wrong. It's very, very close to the correct value in these good models. And actually, if you look at the model predicts, the model predicts a sequence of digits in some base. So you have a sequence of digits in base 24 or in base 32. If you look at the sequence, the correct sequence and the wrong sequence, one thing you will notice is that for the same error in different base, the model will make different predictions. So whereas whether the model is right or wrong doesn't depend on the base, the value predicted depends on the base. And if you look at the digits predicted, there is a pattern, which is the first digits are always correct. The last digits are always correct, which the first digits explain when the ratio is close to 1. And it's in the middle, you have 2 or 3 or 4 digits that are wrong. So you can see here, you got the correct prediction, which in base 24 is 4, 21, 20, 6, 7, 3, 20, etc. and you got the model prediction, and you start with the same five tokens and with the same three tokens, and you got two tokens that are wrong in the middle. And if you look at all the good Bayes, this table, so you got the Bayes that perform the best, that have, say, less than 500 errors. And you have behind that the prediction length. So how long, were the sequence that the model tried to predict. So they depend on the Bayes, obviously. You can see that about half the tokens, or a little more than half the token, usually are correct in all model prediction. And these are sort of evenly split between the beginning and the end of the token. So what happens in the best model is that the model is not randomly predicting. The model seems to know the story, seems to know the correct solution. But when it predicts the token, at one moment it seems to be confused and predict wrongly. And the funny thing is that the decoder is supposed to be autoregressive, so it predicts the first and then the second and the third token. But the model is not wrong in the last token, it's wrong in the middle. So there's something about the decoding which suggests that the model seems to be much better than the accuracy suggests, even though the model is already very good. When you look at the errors, there's this intuition that the model is very close, which again is a bit surprising and seems to be, a hallmark of mathematical transformer. You don't get that in a language task.
There's another
So
question in the
yeah,
chat.
yeah, please.
Oh, it's just me again, Francois. I mean, we would say like it's very natural in the sense that having those top digits correct is kind of like being close in the Archimedean valuation, like
Yeah,
thinking of the integer as a real number, and having the last digits correct is like being close in like the b-adic valuation, like as you
yeah,
say, modulo powers of b. And so it's doing something very natural, number theoretically, right? It's like we have like these
yeah.
local valuations, and that's what it's able to see. So I mean, I'm curious, like I would be curious about if you take like the middle digit, like the one exactly in the center, and you say, if it doesn't get it exactly right, is the middle digit basically a random digit, or is it even somehow getting some learning even all the way in the middle? I mean, sometimes you hit it on the nose, right? I mean, once you capture the classes where you're going to get K and K prime exactly right, then of course it's going to get the middle
Yeah.
digit of that number right. But I wonder in the cases where it doesn't, whether it's kind of all or nothing.
So in this case, I spent a lot of time trying to spot patterns because, I have few enough examples to look at all of them. One pattern I noticed is that usually when the model is wrong, what it says is that it tends to stutter. It tends to output the same digit several times. 88888. You saw that in the previous one. You see you got a pair of eights. And this seems to happen repeatedly. It's not systematic, but it does happen. I couldn't find anything more mathematical, but we could talk about this because there might be a pattern still that could be found in the way the error happened. The way I was surprised, I understand the mathematical sense it makes, but it makes less sense AI-wise because the way the model predicts the token is, from left to right, so large digit to low digits. So it's funny that the model at one moment gets it totally wrong and then somehow falls back on its feet, which suggests that the generative process is not as autoregressive as people think. Basically, the model is pretending to do autoregression and predict from the next, but actually predicts every token more or less independently from the previous one, or the last ones wouldn't be correct. And this is counter to the theory, notably Jan LeCun, supports that, saying, oh, autoregressive models are very limited and they can predict anything. Here you can see that the autoregressive model doesn't really care about autoregressivity, it just predicts from the inputs like a non-autoregressive model. But anyway, uh, so this is a very special case. These are the very best spaces. So now let's look at what happened when you want to have, would predict in odd bases where the results are like 80%, 70%. So then you have a lot of errors. What are these errors? So a first observation on the Collatz long step is that, inputs are odd and output should be odd. Collatz mapping maps, well, the Collatz long sequence maps an odd number onto another odd number. So all the training data that the model sees is odd to odd. Okay, so the model should never be able to predict an even number because it has never seen an even number in the training data. And actually, if you look at the even Bayes, you can see that less than 0.8% of model prediction are even, and it's almost zero for the best Bayes. So yes, the model learns that in even Bayes, the model learns that there are certain n digits that you should never predict, and the model never does that. The model learns from the data. So far, so good. But if you look in odd base, if you look at the model errors, 85 to 90% of model errors correspond to even numbers. I'm letting this sink in because this is very strange, right? Because normally, if the model was randomly predicting one number in two, one error in two should be even. If the model has a bit of, intuition was better than chance, it should be more odd than even because the correct solution is odd. But here, no, the model is predicting way more even number than it should. So it has acquired a bias or some kind of bias. It predicts way too many even numbers, whereas it should never do so. So this was a very, startling observation. And then at that point, you might want to look, what does the model predict? So I'm back to my ratios. In those cases, in odd base, I'm looking at what are the model errors when the model predicts an even number. And you can see that in about 70 to 80% of model errors, the model is exactly wrong by a small power of 2. Instead of predicting a certain value, it predicts twice or 4 times or 8 times or 16 times the value exactly. Okay? And you remember my Collatz long step. You multiply by 3 and plus 1 divide by 2 many times, and then you divide by 2 many times. So ending up with a number that is too large by a power of 2 just means that the model forgot a number of division by 2 at the end. And so 70 to 80% of the errors, and I can prove that, if you look at the data, you can show that this is exactly what happens. The model learns the correct value of k, the first number of loops, but it never overestimates, underestimate the value of k prime. So it forgets to divide by 2 the right number of time. And even more interesting, this happens for very specific value of k and k prime. So practically, if I have a value, you remember my model is learning to predict k and k prime, and it's learning to predict in increasing order of k plus k prime. So first the small values of k and the small values of k prime and so on. So at one moment, if you look at a trained model, it's going to be able to predict k up to a certain value. And for each k, k prime up to a certain value. This is what yields, the total accuracy. Now, my power of 2 errors happen exactly in values of k where the model can predict at least k prime equals 1. And they happen because the model predicts the largest value of k prime it can predict. Okay, so let me show you an example. Let's look at base 27. In base 27, I end up with 71% accuracy. I have power of 2 errors that account for about 3/4 of the model errors. Power of 2 errors are cases where the model predicts 2, 4 times, 4 or 8 times the correct value. Now, the model correctly predicts all the input with k, number of first step equal 1 and k prime 1, 2, 3. K equals 2, k primes 1 and 2, and k equals 3 and 4 for k primes equal 1. That's all the model predicts, and that is what yields the 71% accuracy. Now, the power of 2 happen exactly and only for k equals 1 for k primes larger than 3, and then the model predicts as if k prime was 3. So if k prime was 4, you get 2t. If k prime is 5, you get 4t, and so on. For k equals 2, k prime larger than 2, the model use k equals 2, etc. So there's a pattern. The pattern is that the model, when it falls in like 3/4 of the case for odd bases, so most of the errors in odd bases, is not that the model has not learned the Collatz sequence. It had just learned to do the correct calculation, all the arithmetic calculation, up to a certain number of final divisions, because the model doesn't know that k prime, the number of last loop, can be larger than a certain value. Okay? And so this is what happened. This accounts for about 3/4 of all the errors in odd bases. So we could have a look now at what exactly happens in even bases. And in even bases, you have the same thing, but in even bases, you don't have exactly twice 2t or 4t or 80. It's not exactly the multiple by 2. It's this plus a small number. Why? Because in an even base, the model knows how to tell an even from an odd number, and the model insists on predicting an odd number. So the model will do the same calculation, but get it wrong at the last step in order to predict an odd number. Funnily, if you look at the difference between the correct power of 2 times t that you should have and the correct value, you only have a few values. So typically it's 1 or half, the largest odd number dividing the base. That's so base 26, it's either plus or minus 1 or plus or minus 13 in like 90% of the case. So even in this case, you can predict. And then there's another kind of error that only happen in even base, which is this replica, 1 on 26, where the model is predicting the correct value divided by the base. And this again can be explained. You remember my model is predicting token after token. How does the model say that a prediction is finished? It predicts a specific end of sequence token, which says I'm done. And in this case, sometime this guy comes up one token in advance. So, you forget the last digit, so you divide by the base or by the square of the base or something like that. Okay, so these are the power of two errors, which you see in both even and odd base, and account for, like 3/4, between 70 and 80% of all model errors. So at this point, you can say, okay, in many, many cases, the case where K is not too large, the model errors are completely explainable. Explainable in two ways. You can tell when they happen exactly, and you can predict with a very good accuracy the values that the model is going to predict. Okay, so the next point is, could you predict the rest of the errors? And this is actually the case. So here in base 26 and 27, I removed all the power of two errors, everything I explained. So I'm stuck with about a quarter of the remaining errors. And you can see it's still quantized. And I still have my power laws. But then instead of starting on 2, the power laws start on 2/3 or 4/9 or 8/27, so something like that. So basically what the model is doing is that the model is predicting, instead of being wrong on K prime, the number of last step, it's wrong, it underestimates the number of first steps, so K. Okay, so we have the same pattern happening with where the model is trying to predict two loops. It calculates correctly, but it gets the length of the two loops wrong. So in the previous case, it was getting the second loop wrong, and here it's predicting the first loop wrong and then try to manage with the second. Okay, and if you look at that, and specifically, you can again say what the model does. Basically, this happens for all large values of K. So all value of K where you couldn't predict K and K prime equal 1. And it happens, in that case, you predict the largest value of K you can predict and K prime equal 1. So the best thing you could do, the largest value of K prime, this is what the model predicts instead of the correct value. Okay, so altogether, those two guys predict more than 90% of model errors. So I'm not explaining all the errors, but the model clearly doesn't hallucinate and everything is explainable. So you remember I had a learning pattern. Together with this, I have an error pattern that says that more than 90% of errors can be explained by two cases. One case where the model is predicting, the correct value of K, small case, and the largest value of K prime that it knows how to predict. And the second case where it predicts the largest value of K and K prime equals 1. Okay, so this generalized the learning pattern. I have a learning pattern together with a error pattern. Okay, so I'd like to conclude now. What have we learned from there? So the first thing is that, it opens a lot of perspective, not for collates. I have no ideas on whether what can be done with collates on that. But I think it opens a lot of interesting perspective for mathematicians and especially for number theorists, working with integers or that kind of objects. So there's a lot of things. You can learn arithmetic function by supervised transformers. So there's this idea that, oh, models are bad at arithmetic is wrong. If you train them, they can learn a lot of things. But you can learn a lot of things about your problem just by watching the model. And sometimes you can even learn a lot of things by looking at the errors. The errors can be very insightful. And this can provide a mathematician with intuition. So it's a first experiment, but I feel that this could possibly be a tool for mathematical insight. And the question then would be, okay, can we make this a little more systematic? How do we want to design those experiments? Here I found a problem. I had the intuition that I would like to look at the bases and stuff like that. We did the same thing, with Angelica Babe and people like that doing the same thing with elliptic function, well, with Frobenius sequences and stuff like that. So, there are things that can be done this way, but it would be great to systematize it. A second thing I learned, which I like to call the tacit dimension, the idea that models know more than they can tell, is that, if you look at the model failures and the fact that the model failed for very close to the correct solution and knows a lot of calculation, suggests that the model probably knows, internally, if we could look at the internal representation of the model, the problem knows way more about the problem than what you see when you look at the output and compute accuracy. So it might be a problem of the decoder, it might be a problem, but the internal representation space, so the way the model represent the sequence of inputs, probably holds a lot of rich information. And it would be very interesting to try to probe and design geometric methods to retrieve this kind of information, to know what the model has learned about a problem. This could be a way to learn more mathematics. Um, and of course, if a lot can be done in the representation space, then there's another question more for the AI people is that it could be interesting to design architectures or experiment that foster the learning of such rich representation, which could then exploit to learn the mathematics and stuff like that. Okay, so another way to think of, the lessons here is that I've been talking of AI for math, but there's an interesting consequence on math for AI. You see here, I'm using a math problem that I study well because I have theory, because I can leverage theory that already exists to study how a model can learn. It's usually said that models are black box, they can be explained. Here I can explain very much what the model is doing. And maybe we could investigate what the model is learning, what are the steps in learning, etc. So what I'm suggesting here is that it's quite possible that math problems form very, very good benchmark to understand how deep learning works and how those models acquire knowledge and then use this knowledge in order to maybe develop new models or improve existing models. Okay, the final thing I'll say, I'm a bit off time, is that it's something that I find relatively cute. We've all learned that deep models are universal approximators. There's this old theorem from 89 and 90 that say a neural net can approximate every function as close as you want, so long you make it large enough and you give it enough data. And when you think of universal approximation, you have a loss, you can approximate any function. You think of something, so it's a 1D graph, so yeah, bear with me. But in one dimension, you got that black function you want to approximate, and you think of universal approximation as you start with this red function that is not very good, and then as training goes on, as you move from left to right, you get to closer and closer approximation, and until you get a very good approximation of the correct function. This is what you think when you think of universal approximation. But this is not what we've seen here. What we've seen here, it looks more like that. I'm beginning by having a function that perfectly approximates my model on the beginning of the domain. So here, one-dimensional, it will be more complicated in high dimension. And then as training goes by, suddenly I'm learning larger parts of the definition of the domain of definition of the function. And this is surprising because it's a perfectly valid way to do universal approximation, but it's not an intuitive one, it's a very special one. And there's probably something to be figured out by studying this, learning pattern. Okay, so yeah, so overall, the overall takeaway is that the model is not really learning the full algorithm. You remember I had this two-step algorithm or the complete function. It's learning a series of special case. So the model is more or less doing pattern recognition. It's recognizing different cases of the problem, and then it learns to solve them very quickly. This is the way things seem to learn. So it's not very successful because you don't learn the full algorithm, but it sheds light on how it is learned. There seemed to be a two-step pattern that was observed in previous work. So this is in hindsight, of course. It seemed that the way the model is learning is that it sort of clusters its input space into classes, here according to the binary ending. And then as it clusters classes, it learns to predict those classes and fail on the rest. So the way the model works is, it clusters the input and then learns the problem on classes. This seems to be the pattern. So it would be very interesting to understand how this pattern emerge, whether it's related to the problem and data distribution, and whether it can be controlled. Okay, so this is more what I had to do. If you're interested by the subject, there are two papers I think that are interesting because they follow the same kind of logic, not to do the same thing. So there's this paper of Angelica Babel learning the Euler factor of elliptic curves, and this paper by Coco Huang and Pio Wan that I think will be presented here in 2 weeks. So stay tuned. And well, that's all I had to say. So thank you very much.
Thank you. Well, this is a good time for some questions. Well, maybe I'll start with one. Uh, if you chose a different sort of discrete dynamical system, do you think the steps that you would have found would have been similar, or do you think there's something special about the learning on this Collatz sequence, which is so famous?
So here I very much suspect that the binary thing that is discovered is specific to the Collatz sequence. And the reason why I think it is that I we have a theorem to prove it. So I think what the model is discovering, so it's mysterious, how you can discover a binary ending using from data that are encoded in base 17 or 45 or 63 is in itself, you could do it by summing all the digits, as Jordan said, but it's a bit complicated. So I think the fact that you discover these classes is totally problem dependent. One thing I observed, though, I observed that in a previous paper on the greatest common divisor, was that we had this classification of input into classes. So I very much suspect that the clustering of the problem into classes, relevant classes of problems, is more or less a common fact about all, learning models or learning mathematics from data, at least for discrete problems. The nature of the class, the fact that it's binary and something like that is obviously specific to Collatz. And I don't know if you would have similar theorem. I suspect the Kontorovich and Sinai theorem says that this is more general than Collatz. It's a whole family of sequences that are defined, in the same way in this modular plus multiplication division thing. So I would suspect you would discover similar things. It would be worth trying.